So when we're applying Newton's second law to problems, we're trying to figure out what the forces on the body are going to do to the body, how they're going to move the body, whether they're going to move the body. So we may be talking about a car driving on a road, or a book on a desk, or a pendulum hanging, or an object hanging from a string. So we're just going to talk about all kinds of situations where we have to identify the forces on the body. We therefore identify the net force on the body. We know the mass of the body, and we therefore can figure out the acceleration of the body. Okay? So, and it may be that we want to know, given a set of forces, how fast is the car going. So then we can use kinematics to relate the acceleration to velocity, displacement, and time. But Newton's second law gives us the relationship between force and acceleration for a given mass, or for forces on a given mass. And then we can use other things like kinematics to figure out the relationship to position, velocity, and time. So in order to apply Newton's second law, we understand what acceleration is. We did that in kinematics. We understand what acceleration is. I think we understand what mass is. Mass is just a property of matter. It's a property that matter has. And we say we know the mass of the car is 1,000 kilograms, or we say we know everything else and we want to figure out the mass of the car. So we could go backwards. We could say the acceleration is 2 meters per second squared, and the net force on it is, in order to give that acceleration, is 2,000 newtons. So what is the mass of the car, right? So you could go backwards. But anyway, so F net equals ma gives a relationship between these three variables. We understand mass and acceleration, but net force is the sum of all the forces on the body. We've talked about those forces, but we haven't carefully classified those forces. So in order to know that we are accounting for all the forces on the body, we need to know what forces could be applied to a body. So we need to take a moment to account for all, or to catalog all the forces, all the possible forces. So when we're writing down F net equals ma, we need to be able to figure out what forces are on a body. And so then I ask you the question, think of all the possible forces on a body. We have talked about the weight, or the gravitational force, right? So the weight, which is equal to the gravitational force. That is one force, right? That's the force that holds us to the earth. We'll talk a little bit more about the gravitational force later. We've talked about friction, right? Frictional force, FF, which is friction. That's the force that resists relative motion between two bodies. Whoops, while I'm at it, let's give all of these things a name. We just did for FF, F sub F is friction. Weight, we often, it can be called a lot of different things, but we call it the gravitational force, F sub G, or we call it F sub W, which is weight. Sometimes we just call it W. But whether you call it gravitational force or weight, that's okay. Then we've got the normal force. So the normal force we'll usually call F sub N, which is the normal force. And remember what that is. Do you remember what that is? That is the force due to contact between two surfaces. And it's not because of sliding, but due to contact. So it's perpendicular to the surfaces in contact, as opposed to the frictional force, which is parallel to the surfaces in contact. So again, we're going to spend more time with friction, and friction comes up again in chapter 6 in more detail. So for now, we'll just sort of use friction as a catch-all for sliding forces. But the normal force is the perpendicular force due to contact between two surfaces. And what I mean by perpendicular force is I mean it is perpendicular to the surfaces in contact. If I have a box on the ground, that the surfaces in contact, the normal force is perpendicular to the surface in contact. The floor pushes the box perpendicular to the contact surface. So what other forces can we talk about? We've talked about only really one other force, and that's the pushing force. If I put my hands on something and I push, that can be considered a normal force, but just calling it a push is just fine too. So an arbitrary push or pull. So we call that the applied force. Whoops, I'm running the wrong color. So we can apply a push or a pull by putting our hands on it or something like that. But usually if it's something other than our hands, it's going to be a normal force because we put it on a surface, or the next force, which is a tension, which is where we attach a rope. So another force that we haven't talked about is tension. And that's a force due to a taut, T-A-U-T, rope, chain, cable, etc. Really, you'll see that it's the same as a pull, but it's a special case where we're using a rope or something like that. So, for example, if I attach, let's not do a box. We keep on doing boxes. Boxes are boring. Let's attach a leash to my fish. And so that now I've attached a rope to the fish, right? And so this is my beautiful drawing of a person, and attaching a leash. Now with the leash hanging down in the picture that I have here, there is no tension in the leash. Well, there is a tension due to the fact that gravity is pulling down on the leash a little bit, but there's no tension on the leash until I pull it taut, until I pull it tight, right? So let's go ahead and pull the leash tight. So now I'm exerting a force on the fish due to the taut rope. So hopefully you can see it's really the same as a pull, but we call it a tension. And so when you're pulling something, there's a tension in your muscles. There's a tension in your arm, and you can call that a tension too rather than a pull. So it's whether you call it a tension or pull, that's okay. So does that do it for the list of forces? Let's look. We've got gravity, normal, some applied push or pull, friction, and tension. Are there any other forces in nature? Well, yes and no. Yes. I mean, one, for example, is the spring force, or sometimes more generally called the elastic force, but I'm going to write the spring force. Didn't mean to change colors, but I'm not going to bother doing anything about that now. Spring force is the force due to a spring. And whether the spring is compressed or stretched. We'll talk about that in a later chapter. That doesn't come up just yet, or maybe it comes up later in this chapter. But really, when you think about it, a spring force is really sort of just like a tension, at least when it's stretched. Maybe it's more like a normal force when it's compressed. But we differentiate because we can specifically talk about the nature of the spring force. Now, if you keep thinking about, are there other forces I know of, you may come up with some other forces. Some of them may be real forces, some of them may not be. I'm not standing in front of you, so I don't know, but I would like you to think, really brainstorm and think about what other possible forces are there. There are some other forces that come up in the second semester of physics that we don't use in the first semester of physics. I'll mention them. We've got the buoyant force, F sub B. I always spell it wrong. Buoyant force, and that's due to being submerged in a fluid. We've got the electromagnetic force, or the electric force, and the magnetic force, Fe and Fm. I'll just say electromagnetic force. That comes up in second semester when we're talking about charges and magnets, electromagnetic forces. The force between charges, the force between magnets. This stuff is not Physics 115 topic. But other than that, I'm sure you can think of something you think is a force, but other than that, I can't really think of anything else. Except for the four fundamental forces. Don't know if you're aware of the fundamental forces. This is a really interesting but not really connected subject area, which is that all of these forces we're talking about, buoyant, E&M, spring, tension, normal, gravity, and whatever else was on the other page, friction, etc. They're all really just one of four forces. There are really only four fundamental forces in the universe. And those fundamental forces are gravity, so gravity is itself special, what's called the weak force, the strong force, and the electromagnetic force. They are out of order, EM force. in terms of strength. Gravity is the weakest of them. Electromagnetic is the next weakest, then what's called the weak force and the strong force. And you may care, or you may know, or you may wonder, or you may not care at all what these four forces are. But these are the four fundamental forces in nature. In other words, any force you can think of is one of these four forces. And so the forces that we deal with on a daily basis, the force between the car and the road, the force between the book and the table, etc., they're the forces on the book on the table, or the car on the road, or the airplane in the sky, they're all either gravitational or electromagnetic forces. All of those forces. For example, the normal force is an electromagnetic force. It is a force of repulsion between the atoms and molecules in the objects. And the table is repelling the book. Otherwise, the book would just fall into the table. So really, most of the forces we're talking about are electromagnetic forces. Gravity is unto itself a force. Nothing else is a gravitational force except for the force of gravity or weight. The weak force and the strong force are in the atoms and molecules. We don't deal with them in Physics 115, 116, right? The weak force is a force that has to do with radioactive decay, and the strong force is the force that holds together the nucleons in a what's the thing in the middle of an atom called? Nucleus. The nucleons in the nucleus, but it's the force between protons and neutrons. Force between protons and neutrons. So the strong force and the weak force we don't deal with. E and M force, gravity, we deal with all the time. But those don't matter, because really the only forces we're going to break up the E and M forces into the forces that we are more familiar with, right? So the forces we care about are the gravitational, the normal, the tension, the spring or elastic force, the frictional force, and other applied pushers or pulls that we didn't categorize in these categories. Those are the forces that we're going to care about when we're doing F net equals the sum of all the forces. What are all those forces? All the forces, they're these guys. They're these guys here. Okay. So what does this all mean? This all means that when we're trying to identify the net force on a body in order to apply Newton's second law, we simply ask, this is another place where you have to memorize. We simply ask, is there, one, a gravitational force? Is there, next, a normal force? Is there a rope attached? In other words, is there a tension? Is there a spring attached? In other words, is there a spring force? Is there a frictional force? In other words, is it sliding relative to a surface? And then is there some push or pull that we didn't categorize as a normal or a tension? Some hand attached. So you just got to read the problem and ask that. And then we've taken into account all possible forces. Now, one more thing before we get off of this, and that's that some of you may be thinking, wait, he's forgotten some forces. What about, for example, anything that you name for me, by the way, will be one of the forces we already mentioned, except for the centripetal force. What about the centripetal or centrifugal, which is the opposite, which is something else? But what about the centripetal force? The centripetal force is a force that we're going to be talking about. My screen keeps changing size. I don't know what's going on. And the question is why didn't I include centripetal force in that list? This is a super important point. Super duper important. Centripetal force is not an additional force in that list. The centripetal force is one of the forces in that list. It is a name for the force that makes something go in a circle. So, for example, think about a body that goes in a circle. Let's take, for example, a car going around a corner. A car going around a corner. So think about that car going around a corner. If the car is going around a corner, then there must be a centripetal force, at least, there must be a centripetal force, a force pushing it towards the center of the circle. We're just assuming that it's approximately circular. It doesn't matter if it's circular or not. There's still a centripetal force. There's still something that has to go perpendicular to the motion in order to make something turn around a corner. So the acceleration is towards the center of the circle. So therefore, there must be a force towards the center of the circle. Remember, we call if it is circular motion, we say that's the centripetal acceleration, centripetal force. If we can approximate it as circular motion, or if we can just take the component of the force that is making the car turn. It must be centripetal force. So the centripetal force is the thing that makes the car turn. So is the centripetal force a new force? Is it something that we've just discovered? It's not, right, we've made our list of forces, but is it another force to add to our category? And the answer is no, it's not. Because what is the force that gives you the centripetal acceleration, or that gives you the centripetal force? The force is friction, right? So friction is the centripetal force. In other words, all we're saying is friction is the force that makes the object go around the corner. If there was no friction, the car could not go around the corner, right? It's friction that's holding the car to the road and keeping the car from slipping. So friction is the force that makes the car go around the corner. Friction is the force that makes the car go in the circle. So friction is the centripetal force. Centripetal force is not an additional force. Take another example. Let's take a ball on a string. Not a perfect picture, but let's say I have a ball on a string and I'm whirling it in a circle, right? So that ball is going, its velocity is always tangential, its acceleration is always inward. And because it's going in a circle, it's changing direction. There must be a centripetal acceleration. That centripetal acceleration, therefore, arises from a centripetal force. There must be a force that is causing the ball to go in a circle. Do we call it centripetal force? No. The centripetal force is the force that makes the ball go in the circle. What force is making the ball go in the circle? Think about it. What is attached to the ball that's keeping it in the circle rather than the ball just going off in a straight line? It's the string, right? So in this case, the tension is the centripetal force. F sub t, the tension in the string, F sub t, the tension, I don't need to write it twice. The fact that there's a taut string attached to the ball, that's what's giving the centripetal force. So you can imagine that all of our forces could be centripetal forces if there's something that makes an object go in a circle. So for example, let's go back to our list. Fg, can the gravitational force be a centripetal force? And the answer is absolutely yes, the gravitational force can be a centripetal force. Because, for example, the moon. Why is the moon going around the Earth? The moon is going in a circle. So there must be some force pulling it towards the center of the circle, and that's a gravitational force. So gravitational force is the centripetal force for the moon. Can the normal force be a centripetal force? This one, absolutely it can. It's a little less common, but I'm trying to think of a good example. The example I always use, and it's easier if I'm in front of you, is the amusement park ride, the Barrel of Fun. In the amusement park ride, the Barrel of Fun, let's go ahead and draw that. Let's see if I can draw this. I don't know if you can tell what I'm drawing, but it's a round room, and you walk inside the room, and you stand against the wall, and the room starts to rotate. The room starts to go around at some high frequency, relatively high frequency, and you get pinned against the wall. And getting pinned against the wall means that there's a normal force between you and the wall. If the wall wasn't there, you would just fly off tangentially to the room, but the wall is there, and it's that force due to contact between you and the wall that's keeping you moving in a circle inside the room when this room rotates. It's an amusement park ride that you don't get at too many amusement parks anymore. Guess I'm showing my age. But that's an example of where the normal force, it creates a centripetal force. So in that case, the normal force is the centripetal force. So back to our list of forces, we've seen where tension can be a centripetal force. A spring, the rope is just like a spring. You could attach a spring to an object and rotate it in a circle, and the spring force would be the centripetal force. Friction, we've seen that. That's where the car is going around the turn. Okay, so the centripetal force is not a force that belongs in Fnet or belongs in as one of the sum of all the forces that belongs in your free body diagram, because the centripetal force is just the force of this list of 6 forces, 6 including an applied push or pull. It's the force which causes the thing to move in a circle. So first of all, let's define our forces. I'm not actually going to spend a lot of time defining them, but the first one, the gravitational force or the weight, Fg or Fw, that is equal to the mass of the body times the acceleration due to gravity, right? Because what we mean by weight is if we take an object and the only force on it is the gravitational force, if the only force on it is gravitational force, in other words, the body is in free fall, right, what will that force be? Well, if F net equals ma, then the force is going to be m times the body's acceleration, and the body's acceleration is 9.8 meters per second squared, or g. So the weight is defined as mg. So mg is the weight of the body, and the direction of the weight is towards the center of the Earth. If we want to put a vector sign on it, right, it's mg towards the center of the Earth. That is the gravitational force between the Earth and a body. Now, be careful, because, right, if we're on the moon, there's a gravitational force between the moon and the body. And actually, don't forget that there's a gravitational force between any two massive bodies. There's a gravitational force between me and the desk in front of me. We attract each other gravitationally. It's just a lot smaller than the gravitational force between me and the Earth, because the Earth is so much larger. So there's gravitational force between any two massive bodies. So if we move off of Earth, we got to be careful about what we're talking about in terms of weight or gravitational force. But on Earth, the gravitational force is defined as mg. The tension, on the other hand, we can't define it as anything. It's what's called a reaction force. It's a reaction to the other forces in the picture. So we can only figure out what tension is by solving Newton's second law. So we can only figure out what tension is by either telling you this is what the tension is, or by solving Newton's second law. Same thing with the normal force. We actually saw this when we first defined normal force, that the normal force is a reaction force, usually gotten to by solving Newton's second law, because a box on a floor, if the box has a weight of 150 pounds, then it's pushing on the floor with a force of 150 pounds if it's not moving, and the floor is therefore pushing back on it with a force of 150 pounds, and the normal force is 150 pounds. But if I push down on that box, this was the example we did in class, if I push down on that box, if I add an additional force in the downward direction, then the normal force compensates for that. And so even though it's a 150-pound box, if I'm pushing down on the box with an additional 50 pounds, then the normal force must be 200 pounds. We'll do an example showing that in a second. It's a reaction force. Okay, the frictional force we will define later. Right now we have a sense of what it is. We will define it later. And same thing with the spring force. They actually have equations that we can deal with, but we'll define them later. Okay.